Swayam Prabha. Digital India. Educated India.
Hello, welcome to Astrochemistry. This is lecture 12 and it's also tutorial 2. So in the last lecture, that is tutorial 1, we had looked into a series of true or false type questions. We were starting with some general knowledge type factual questions. We also looked into various physical and chemical concepts such as red shifting, blue shifting of light, and the properties of the interstellar medium. What about comets and meteorites, etc., etc. So we'll continue with our problem solving session in this tutorial also, and moving beyond true or false type questions, we'll look at some other types also, some numericals, some conceptuals, etc. Okay, so the first question in today's tutorial session is going to be, this is page 1. The first question is going to be, now you all aware of the idea that hydrogen absorption lines can be measured in a spectrum, correct? You take a hydrogen atom and its absorption spectra, the lines can be emitted. The lines can be measured. We've all seen about the hydrogen atom spectrum right from class 12. We're talking about the Lyman, the Balmer, the Paschen, the Fund series, etc. Okay, so the hydrogen atom spectrum, right? Yeah. So H atom absorption lines measured at, okay, on Earth, they have been measured at 4861 angstrom and 6565 angstroms. Okay, so these are the wavelengths at which that the hydrogen atom absorption lines have been measured. All right. Now, from a distant star, okay, from a distant star in another galaxy, okay, this is on Earth. So from a distant star, in another galaxy, the same hydrogen atom absorption lines are measured to be, I'll just take a look at the exact values, 4923 angstroms and 6647 angstroms. Okay, so this is the data given to you. This is given, right? So based on what is given to you, the questions are: A, is the galaxy, is the galaxy from which we measure the, not our galaxy, okay, the other galaxy, is the galaxy at rest or is it moving? What do you think is the answer? Is the galaxy going to be at rest or is it moving? Well, based on our discussion about how Hubble considered the universe to be expanding, there is clearly a shift, right? If the galaxy were to be at rest, the hydrogen absorption spectrum should be exactly identical. It should be, if it's 4861 angstrom, the same line should also be measured at 4861 angstrom. However, in this case, they are different, correct? So the fact that they are different tells us that it is moving. It's a straightforward answer. Okay, having answered this, the next question is the galaxy moving towards us or away from us? Is it moving? towards or away from us? What is the answer? Well, for that, you need to look into the magnitude of the wavelengths, right? Just in the last class, we discussed about red shifting versus blue shifting. And what is the characteristic of red shifting? The wavelengths increasing, correct? That's what's happening on Earth, where you would expect, the lines to be at 4861 angstroms. It has shifted further red. That is somewhere towards like 4923. And similarly for this line also, there's a uniform shifting of the lines. Okay. So the red shifting is noted. So it is, of course, red shifted, and therefore we understand that the galaxy is moving away from us. Moving away. Okay. So we have sorted this. The next question is going to be that there is something called as a Z factor. I haven't told you about this. Find out the Z factor. Now, I've of course not introduced the idea of the Z factor yet in this course. So the Z factor is a measure of by how much the galaxy is redshift, the galaxy is moving away from us. It is a quantitative way to measure the extent of redshift. Okay. So that being said, the Z factor is given by the wavelength of the galaxy, right, minus the wavelength of the wavelength of the galaxy minus the wavelength that you would encounter when it is at rest. That is, the wavelength for the absorption line on Earth divided by, okay, right, divided by the wavelength assuming it is at rest. So this is the formula. We can just substitute it, right, and we can calculate the Z. For example, for this series of lines, this 4861 and 4923, the Z is going to be therefore, 4923 minus 4861 divided by 4861. Okay. And can you quickly do this calculation and tell me what is the magnitude of this number? This is what? This is like 62, right? 3 minus 1 is 2, and 12 minus 6 is 6, and the rest of it get cancelled out. So this is going to be 62 by 4861. We'll calculate this in a bit. Okay. Similarly for the other line, I'm just calling it Z1 for the first line, and then Z2 for the other line is going to be what? It's going to be this minus this divided by this. So it is going to be 6647 minus 6565 divided by 6565. These units are in angstroms and this is a ratio, so therefore, it gets cancelled out. So the Z factor has no units. Okay, and so this is going to be what? So this is going to be 6565. 65. Okay, actually I made a small typo. This should be 6563 here. It won't make a big difference, but 6563. So the 7 minus 3 is going to be 4, and 14 minus 6 is 8. The rest of it get cancelled out, and this is going to be 6565. And what are these two numbers? I'll let you to calculate it yourself, and the number is going to be approximately 0.012, correct? Yeah, you can approximate it to 0.013. Yeah, round it to this many decimals. It's the same here. And notice that both Z1 and Z2 are the same. In other words, we understand that for both the lines, the shifting is uniform. Okay. So what is the idea behind this Z factor? It lets us quantify the extent of the shift. Okay, and here it's a redshift. So this redshift is uniformly happening for both the lines by this magnitude. All right. Now, from this Z factor, okay, we can do one more thing. I will delete this part. I'll keep the data intact in page 1. Okay. Now, from this, okay. From the Z factor, find out how fast the galaxy is moving away from us. So what is the answer? Well, let's say that you have no idea at all. Let's say that you have no idea at all, and we have no idea about any formula. So what would be an intuitive guess? What might you, like, for example, without knowing any formula, just looking at the Z factor, I'll give you the hint. The hint is that the Z factor can help us, determine this number. And I haven't introduced any formula at all to you about calculating this thing, right? So how do you still calculate it? Yeah, in one sense, it makes, it kind of gives us an idea that, hey, somewhere these galaxies are all moving. So the speed of light should be involved in some way, right? We don't know how yet. Okay, we don't know how yet. And this factor is unitless. It has no unit. So it can be also thought of as the ratio between the speed at which, the galaxy is moving divided by the speed of sound itself. I mean, see, can it be the other way about? Logically, it cannot be, because nothing exceeds the speed of light, right? That is our current understanding of cosmology, okay? Based on our current understanding of cosmology, nothing can exceed the speed of light. So, because Z is something containing no units, this is also meter per seconds in SI units. This is also meter per seconds. They get cancelled out. All right? So based on this formula, I just without giving you the formula explicitly, I just taught you to think about formulae, okay, right, and how they make sense. All right. So that is how we get this formula. Now that we know the Z factor, which is approximately 0.8 I mean, it's like this number, right? Yeah, 1.3 10 to the power minus 2. It's a very small number. And we have the speed of light, which is what? 3 into 10 to the power 8 meters per second. So once you substitute it, what answer do you get? Just check and verify if you get the following number. It's approximately 3826 kilometers per second. Okay. I mean, you can take care of the unit. Okay. 1 meter is 10 to the power minus 3 kilometers. So just make sure you do that modification, and this will be 3826 kilometers per second. Are we fine with this? Now, one last point, okay? I will, we no longer need the data, so I will make this page number 5. So, let's see, the question is, normally, when we talk about starlight coming from a distant galaxy, we talk about these galaxies moving and all that. We have to, in some way or the other, include ideas of relativity, correct? So, in the following discourse, in questions A through D, we never included the idea of general relativity at all, or special relativity. We completely discarded relativity. We discarded relativistic effects. The question is it a valid approximation or not? What is going to be the answer? Is it valid or not? Now, here, of course, we need to take a look into the answer and then address this issue. When does when do relativistic effects become predominant and important? It happens when particles travel at the speed of light. okay, or close to the speed of light, as we tends to see. But look at this number. This number is significantly lower. Is significantly lower, right? So therefore, we are justified. We are pretty much justified in not including relativistic corrections. Of course, justified. Cause V is significantly less than C. It's small v. Okay. Are we clear? So, I mean, you can ask me another question. That is, in the first place, we did not include relativity and then found this number. What if after including relativity, the velocity happens to be very high? What is the answer to that? The answer to that is that this number is still extremely small with respect to the speed of light. So even after including relativity, the order of magnitude, in fact, I did some injustice by only including 2 signs. It should be strictly so many more, like less than signs. Okay, so this tells us that relativistic corrections are not important for this problem. Are we good? So we now move on to the next question. So, and this will be question number 2. The question is, it kind of, some of you must have, you would have definitely answered this question had you been in high school, but at college you may have had some confusion with some basics. Okay, that's why I'm emphasizing on this question. It is, what is the difference between a hydrogen and a proton? Okay, and as part of it, yet another question is going to be that, in Big Bang nucleosynthesis, was deuterium, which is what is deuterium? It is the isotope of hydrogen. It's 2H1, right? Was deuterium formed from a proton or a hydrogen? Okay, so are the questions clear? The first question is, what is the difference between a proton and the hydrogen atom itself? I'll make it clear. A hydrogen atom. Oops, I apologize for my handwriting. Yeah, a hydrogen atom and a proton. All right. So the question is, are they the same or different? And the next question is, in Big Bang theory, was D formed actually from a proton or a hydrogen? Now this question, right? Based on the answer to the very simple question here, this highlights a conceptual novelty, okay, which I'll be explaining very soon once we discuss the answer. But the answer to the first question should be very easy. What is it? It is that the hydrogen atom and the proton are of course different. And what do they differ by? They differ by an electron. So H atom okay, right? An H atom, especially when I consider this isotope, I'm considering the 1H isotope, which has 1 proton and no neutrons. Okay, 1H atom, it contains, what does it contain? 1 proton and then 0 neutrons and 1 electron. Okay, this is the 1H atom. But when I say proton, it of course has 1 proton it has 0 neutrons, and the answer should be obvious now, it has 0 electrons. So the proton is nothing but the H atom alongside stripped off the electron. Okay, this distinction is very clear to all of us. However, the next question is where it becomes tricky. In nucleosynthesis, was the proton? When we discussed it in earlier lectures, did we discuss the formation of the deuterium, which is like the 2H1 isotope of a hydrogen? Was it formed from a proton or the hydrogen atom itself, or a hydrogen? I'll retain the question here. So I'll make page 8 on this side. So deuterium, which is 2H1, what was it formed from? What was the reaction responsible for it? If you recall your previous notes, the reaction was that I gave was 1H1 plus neutron giving 2H1 plus gamma rays, correct? And this is how deuterium is formed. And this is the hydrogen isotope, which is also called as protium. Okay. So is it actually is it the hydrogen atom, or is it the proton itself? In the lecture itself, I want to clarify something. I did not do a very good job of explaining this with clarity. Okay. That is why I'm addressing this point in the tutorials again. The actual answer is that this is the proton and not the H atom. So please be clear about this. And this is the deuterium nucleus. Okay. Electrons are not coming into the picture here. I did not clarify this point. Okay. And I may have used the same notation, 1H1, to represent the hydrogen atom as well as the proton in the lecture. I believe it was lecture 3 or 4. But please, I clarify right here. Okay, as far as the Big Bang nucleosynthesis is concerned, electrons are not even involved. This is just the D nucleus, and this is the H nucleus. That is the protium nucleus, and this is the proton nucleus. This is the proton and not the H atom itself, whereas this is the deuterium nucleus, bereft of the electron. All right. So I will clarify this further. I will not delete the question. Why is this concept important? Why do I ask you to pay attention to what looks like a very simple idea? It is that, see, on Earth, when we usually use the symbol for elements, for atoms, when we use the symbol like something AXZ, A is going to be the atomic number, A is going to be the mass number, which is defined as number of protons plus number of neutrons, correct? And your Z is the atomic number, which is equal to the number of protons, and for neutral atoms, it's also equal to the number of electrons. All right. But when we consider the Big Bang nucleosynthesis, the electrons do not even come into the picture here. Please understand. Okay, we are just worrying about how the nucleus themselves are formed. Okay, nuclei themselves are formed. So for the deuterium, for this deuterium atom, which needs one proton and one neutron, right? The fusion of the proton and neutron happens to form the deuterium nucleus. The electrons are not involved at all into the picture. Okay. So what happens is that after the nuclei are established, the nuclei are formed, subsequently the nuclei get attached to the electrons. So the overall message is that, note, in Big Bang nucleosynthesis, electrons are not even in the picture. What do we mean by electrons are not in the picture? I am referring to the idea that we are only talking about the nuclei getting formed. Okay. So therefore, if you apply, what you learned in your high school, the AXE definition, here, the number of protons is not equal to the number of electrons. So there are no electrons at all into this picture. I did not clarify this in lecture 2 or lecture 3 perhaps. Okay, I think lecture 3. Please make sure that you have a thorough idea of this. The key understanding, the punchline, the tagline is that in nucleosynthesis, electrons are not even in the picture, and do not confuse this notation. This notation of like the mass number and atomic number. Here, this does not refer to the number of electrons. The electrons are not even involved. This is just the number of protons. Okay, and this is the number of protons plus number of neutrons. And in the proton, in both the proton and the protium, which is the hydrogen atom, the 1H1 isotope, you have no neutron. Whereas in deuterium, you have one neutron and one proton, of course. I hope this message is clear. Okay, so based on a seemingly simple concept, we understood a very profound idea that in nucleosynthesis, especially under Big Bang conditions, the electrons are not involved at all. Once the nuclei are formed, then subsequently, the nuclei get attached to the electrons. All right, so that was the message behind this question. We shall now move on to the next question. Okay, we started off with explaining in some lecture, we were discussing about the validity of PV equals nRT at various conditions in the ISM, correct? Now this question is, why is PV equals nRT only an approximation at approximately, let's say T equals 10 Kelvin in the ISM. Okay, so what I've written is, why is P equals nRT only an approximation at T equals 10 Kelvin in the ISM? What is the answer? This question tells you how we are only dealing with approximate figures when we use such equations. It is based on our fundamentals, right? What is the answer? The answer is that, well, this is of course the ideal gas law, and the ideal gas law is valid. Is valid under what conditions? It is valid under low temperature, low pressure, and B, high temperature, correct? Why is that? It is because we ignore the size of the atoms or the molecules involved as part of the ideal gas, and we also ignore the interactions between various molecules in the ideal gas model, correct? At low pressure, the interaction and the size effects are taken care of, because when the pressure is so low, there is no need for any interaction. Similarly, at very high temperature, when the kinetic energy is extremely high, right, the molecules need not have any interactions at all. So both the size and interaction effects from our high school level understanding of ideal gas are taken care of. Okay, now what is the temperature we are talking about? It's 10 Kelvin. It's pretty low, right? So 10 Kelvin is rather low for the ideal gas equation to be exactly holding good. And that is why it's only an approximation at T equals 10 Kelvin. Now, what does this question highlight? It highlights two important facets. One is that the ideal gas equation, which we used in the class to determine the number density, is only an approximation, point number one. But nonetheless, B, even this approximate model gives us, excellent estimates. So just because some idea is an approximate idea, we need not discard it in science. This is the bigger picture, the larger philosophy behind our discussion. Okay, so this is an approximation overall because the ideal gas equation is not valid at T equals 10 Kelvin. So how do you rectify the situation? If you want to calculate the exact, let's say you want to calculate any parameter from this equation, give another 4, right? Give another 3, sorry, R is a constant. Okay, how would you do that? That would be done by assuming, various equations of state. What can you think of? You can think of the van der Waals equation of state. One can imagine about, the virial equation of state, where once you find out the virial coefficients, you can compute the parameters necessary. Okay, but the idea is that it is only an approximation. All right. So on that note, in this tutorial, in tutorial 2 that is, we looked into 3 questions. The first question was about some quantitative aspects about the Doppler shift, that is the red shifting versus blue shifting. In the next question, I made you understand that the electrons are not an important part of nucleosynthesis. And in the third question, we saw that the ideal gas model is only an approximation. We shall continue further with more questions related to the ideal gas models and other questions in our next tutorial. Okay, thanks a lot. Have a good day.